In this lesson, we're going to take another look at limits, this time not so much in the context of continuity, but just limits in general and as they relate to rational functions. Just as a reminder, I've put up on the screen the properties of limits. These are things that you should be familiar with from previous math courses. So we know that the limit as x approaches a for any constant k is just going to be that constant. The limit as x approaches a of some function x will just equal a. We substitute the value in. Now, these are the ones where we have to think a little bit more. So if I have two functions and I want to compare the limits and I'm adding or subtracting those two functions, well, the limit as x approaches a of those two functions added or subtracted together will be equal to the limit of each one taken separately. If we have a constant multiplied by some function, the limit of that function as x approaches a will just be the limit of that function times that constant c. If I have two functions that are multiplied together, the limit as x approaches a of those two multiplied functions will just be the limit of each one multiplied together. Same thing when we're dividing. If I have two functions, f at x and g of x, and I'm dividing them, the limit as x approaches a for those two functions will be equal to the limit of the one on the top divided by the limit of the one on the bottom, provided that that bottom function doesn't equal 0. And that's actually what we're going to lean into today, is this bottom function not being able to equal 0. I think the best way for us to examine this is to look at some examples. So we're going to look at this example first, but let's just think. So when you evaluate a limit, we're really determining the behavior of the function as it gets close to the x value. So what happens to y as x gets closer and closer to some number? In functions, you would have had rational functions, and you would sketch its end behaviors. You'd find the asymptotes, the intercepts, and you'd use the idea that there are some values that are impossible. Those are the limitations. And we're going to use that idea of limits to explore the behaviors as a function gets close to specific values. So let's look at this example. So let's look at x plus 1 over x squared minus 1. So the first thing that I'm going to do always with these is try direct substitution, just to see, what are we dealing with? So if we use direct substitution for this first one, as x is approaching -1, I'm going to substitute -1 wherever there's an x. So -1 plus 1 is 0. -1 squared is 1, minus 1 is also 0. That's not so good. We don't really want to divide by 0. Let's try the same thing for the second part. So now as x approaches 1, we're going to substitute 1 everywhere there's an x. So 1 plus 1 is 2. Okay, that's not looking too bad so far. But now I have 1 squared, which is 1, minus 1 on the bottom, which is 0. We don't want to divide by 0. In fact, we can't. It's indeterminate. So dividing by 0 is bad. That's indeterminate. I'm not 100% sure I just spelt that right, but we're just going to go with it. So how do we deal with a denominator that equals 0 in a rational function? Well, we try and factor the problem out. Like quite literally, we try and get rid of what's making it equal 0 on the bottom. So back to our function. We have x plus 1 on the top, and I have x squared minus 1 on the bottom. I can factor that x squared minus 1 on the bottom. So I have x plus 1 on the top. As I factor the bottom, I get x plus 1, x minus 1. We have x plus 1 now both in the bottom and the top, or in the numerator and the denominator, which means we can eliminate it. And that leaves us with 1 over x minus 1. So I think we can see with this 1 over x minus 1 that x cannot equal 1. So when we have this positive 1 situation, x cannot equal 1. So how would we write about that? Well, we would say that 1 over x minus 1, x cannot equal 1 because it does not exist when x equals 1. So the limit itself does not exist when x equals 1. Now, what about when x is approaching negative 1? So what if we have the other situation now where x is approaching negative 1? Well, the limit as x approaches negative 1 using of 1 over x minus 1. We're just going to use direct substitution again. 1 over negative 1 minus 1 gives me negative 1 half. This is okay. This tells me that the limit does exist here and that my limit as x approaches negative 1 is negative 1 half. What does this really mean? Well, it just means that as x approaches negative 1, the y value approaches negative 1 half. Let's look at another example. This one has a square root in it. So the very first thing that we're always going to do is always try direct substitution. So always try direct substitution. Okay, so we're going to try direct substitution for the limit as x approaches 4 of root x minus 2 over x minus 4. So by direct substitution, I have the root of 4 minus 2 over 4 minus 4. I'm seeing a problem already. So I end up with 0 over 0, and again, this is undefined. So in this situation, we cannot use direct substitution because we don't want a 0 on the bottom. And whenever you have a radical, you need to multiply by the conjugate. So the conjugate of root of x minus 2 is root of x plus 2. This is the conjugate. So I'm going to rewrite this as the limit as x approaches 4. We have root of x minus 2 over x minus 4. Now, this is where the mathematical magic sort of comes in. I'm going to multiply both the top and the bottom by the conjugate. So I have the root of x plus 2 over the root of x plus 2. Mathematically, nothing has changed here. This is just equal. This is just equal to 1. So I'm really just multiplying this whole thing by 1. So let's rewrite that out as we now have root of x minus 2 times root of x plus 2 all over x minus 4 times root of x plus 2. So now, instead of eliminating out, because that's just going to put us right back where we started, we're actually going to go ahead and FOIL the top. So we're going to FOIL it. So x squared times x squared leaves us just with x. And I'm just going to write that down here. The root of x times 2 gives us positive 2 root of x. I think I just said that x squared times x squared. I meant root of x times root of x equals x. The root of x times 2 gives us 2 root of x. Now we're going to do the other two. So negative 2 times the root of x gives us minus 2 the root of x. And negative 2 times positive 2 gives us negative 4. Nothing has changed on the bottom. We have x minus 4 times root of x plus 2. So now we can see that the positive 2 root x and the negative 2 root x cancel each other out. So we are left with the limit as x approaches 4 of x minus 4 over x minus 4 times the root of x plus 2. We have x minus 4 in both the numerator and the denominator, so they can cancel each other out, and that leaves us with 1 on top all over root of x plus 2. Now we can use direct substitution. We're not going to get a 0 on the bottom. So if we plug in direct substitution, so the limit as x approaches 4 is equal to 1 over the root of 4 plus 2 gives us 1 over 2 plus 2, which gives me 1/4. So this limit does exist, and what this is telling me is that the limit as x approaches 4 is 1/4, or y is approaching 1/4. Okay, here is another one. Maybe you might want to pause the video and see if you can figure this one out. Do you remember what you need to do if you have the absolute value? So pause it and then come on back. Okay, so we have the limit as x approaches 0 of the absolute value of x over x. We cannot use direct substitution because if we do, we simply get 0 over 0 again. And what's that going to be? Well, it's undefined, so we can't just plug it in. So we need to determine the limit for this one from both the left side and the right side. And remember in the last lesson, we did look at that a little bit. So let's start with the left side. So remember, when I'm saying the left side, what I'm really meaning is that the limit as x approaches 0 from the left-hand side, or the negative side. And that's equal to the absolute value of x over x. So we're going to choose some point that's just a little bit to the left of 0, and I'm going to choose negative 0.1. So we have the absolute value of negative 0.1 on the top divided by negative 0.1 on the bottom. Well, the absolute value of negative 0.1 is just 0.1. And that's over negative 0.1, which gives me a value of negative 1. This is the left side limit. So this is the limit as x approaches 0 from the left of left of the absolute value of x over x. Now, what about the right-hand side? So the limit for the right-hand side as x approaches 0 now from the other side, from the positive side. And again, I'm just going to pick a value that's just to the right. So since we use negative 0.1 for the left-hand side, let's use positive 0.1. So positive 0.1, absolute value of positive 0.1, all over positive 0.1. So we end up with the absolute value of 0.1 is just 0.1, all over 0.1. We end up with a positive 1 value. This is the right side limit. So now, remember, if the left side and the right side don't equal each other as we approach a value, that means the limit does not exist. And we would say that the limit as x approaches 0 from the negative side, root x over x, does not equal the limit as x approaches 0 from the right-hand side, x over x. Therefore, the limit does not exist. And they won't always. So the limit as x approaches 0, it does not exist. Let's look at one last example. I'm going to walk you through this one just in case you don't remember what to do with a cubed root. So we have the limit as x approaches 8 of x raised to the power of 1/3 minus 2 over x minus 8. Now remember that that is really saying that that is the root of x, the cubed root of x minus 2 over x minus 8. That's really what this means. So we could write it as to the 1/3, or we can write it as the cubed root of x. We need to find some way to cancel the factors or get the x minus 8 out of the denominator, because if I do direct substitution into here right now, I'm going to end up with 0 on the bottom, and we don't want that. So how do we deal with this? Well, I want you to recall the difference of cubes. So we're going to use that idea of the difference of cubes to try and get that x minus 8 out of the bottom. So the reason that this is going to work, and we need to think about this for a second, is if I have, so on the top I have the cubed root of x, and on the bottom I have x. Well, it just so happens that if I were to cube the cubed root of x, that equals x. So if I had the cubed root of x cubed, that equals x. Well, guess what? The cubed root of 2, or the cube of 2, is equal to 8. So I am able to use this idea of a difference of cubes. So just as a reminder, our difference of cubes tells us that we have a cubed. If we have a cubed minus b cubed, which we do on the bottom, I can factor that out as a minus b, and I think we used this in the last lesson. And then I have a squared plus ab plus b squared. So we need to figure out what's a, what's b. Well, my a is going to be x, so I have x, and then my b is going to be 8. So now we can go ahead and we can fill this in. So I have, yes, I did that part already. Now we can try and factor at the bottom. So what do we have? Well, on the bottom of this, I'm going to factor this out with the difference of cubes. So I end up with 3 root x minus 2 times cubed root of x squared plus 2 times the cubed root of x plus 4. So remember, this is just my a squared plus ab plus b squared. So now we can cancel out a 3, I better rewrite at the top too, 3 cubed root x minus 2. So now I have a cubed root of x minus 2 on the bottom and the top. I can cancel those out. That leaves me with my limit as x approaches 8 of 1 over all of this other bit at the bottom. So we are left with, the cubed root of x squared, I'm going to rewrite that as x to the 2/3 because that's equivalent, that's the same thing. I have 2 times the cubed root of x, and then I have 4 on the end. So now we've simplified it, we've rewritten it. Now we can go ahead and do our direct substitution of 8. So I have 1 over 8 raised to the power of 2/3 plus 2 times the cubed root of 8 plus 4. That equals 1 over 4 plus 4 plus 4, which gives me 1 over 12. 1 over 12. So my limit as x approaches 8 for this function is going to be 1 over 12, or my y value is going to approach 1 over 12. Now, the homework questions for this particular lesson look a little bit different, and I wanted to talk about that for a second. I have pulled some questions from a different textbook, and I just need to find my piece of paper where I wrote down which questions they are. I think specifically what I would like you to take a look at are, well, do as many as you feel you need to, but at a minimum, I would do question 7, I would do J, let's do M, N, I, sure, L, and then give a couple of these other ones a try as well. The answers you will find are on the next page, or the solutions are on the next page. And have a great afternoon.